Still there.
Yeah.
Take it away.
Sure. So howdy, everybody. My name is Chad. I work at Temporal, and today we're going to talk about building a distributed async IO event loop. So if you thought that this was going to be a talk about async IO just normal, high level, no, it's actually going to be a little bit lower level, and I don't really know why anybody would want to do this except for like a company like Temporal, but it's pretty interesting, and you might learn a couple things about async IO along the way. So we'll see. First, I'm going to explain kind of what async IO is from a high level, and then a little bit about how it works. And then I'm going to have to like jump off into explaining what durable execution is, kind of like what Chris did before with generators, just to explain why we needed to make a distributed durable async IO event loop. And then I'll jump into like what we actually did. And I won't get too deep. There's not too many code samples, not even a demo or anything. And then I'll explain at the end some gotchas that we hit that were kind of surprising to us. So first of all, what is async IO? So async IO is coroutine scheduling on a single thread is basically all it is. Now, a lot of people know this as green threading. You'll see it in all sorts of other languages. Like in JavaScript, it's promises. It's only one thread over there anyways. Java has recently introduced virtual threading, and .NET or Ruby also has fibers. And the way that they chose to implement it is where you can't really see the coroutine implementation. So like in Ruby, if you're doing a sleep and you're in a fiber context, that you won't know that you're sleeping a fiber versus a thread. But Python chose a little bit of a different route. They make it more explicit. They color it, if you will, more clearly. So that's why you have time.sleep versus asyncio.sleep, and they're completely not the same. Don't use time.sleep in your async IO. You'll run into some issues. And unlike some other languages like Java and .NET and Go, Python doesn't do it in like an M&N style way. So it doesn't multiplex the coroutines across threads. It is just in a single thread. But for the most part, that is plenty fine. So it works fairly well if you understand it and if the libraries that you happen to be using work well with it. So there are a lot of gotchas, and I'll discuss most of them at the end, but one of the more obvious ones is that Python is in a sometimes I'm threaded, sometimes I'm async kind of world right now. And using thread blocking things inside of an async defined function is a big problem because it will stop down the entirety of the running loop. Nothing can continue. There aren't even really great tools to detect this these days, and we'll get into that in a little bit. But just know that Python effectively requires coloring of something that needs to await by obviously marking it as async, but not all functions that can run in an async have to be colored, and that's where it gets a little confusing for people. But I'm not going to get too much into general async IO. We're going to get into a little bit how the event loop works and what we did to customize it. So here's a stupid, simple async IO example, right? So you see the non-async version here at the top that's basically do this thing every so often. It's a while loop. It sleeps. It does a thing. Eats an OS thread, right? And you see the equivalent of the exact same thing in async IO. It sleeps, it awaits a sleep and awaits the other thing. So you can run, thousands of these inside of a single thread without any real issues, depending upon what they're doing, that they're not CPU bound. So that's one of the benefits of async IO. I know it's kind of obvious, but it's a good table setter to understand that time.sleep while blocking a thread, async IO.sleep does not. And actually, if you saw Chris's talk earlier, it's actually all powered by generators under the hood, but we won't go that deep. So when we see that async IO sleep, what is it actually doing? Like if I run await async IO sleep, what does the sleep call look like? Like what does the implementation look like? And you can just go into the CPython source and look, most of async IO is pure Python. So I just snatched this out of the CPython repository. So I removed a little bit of validation at the top, but you see that it does a few things. So first of all, it grabs the running loop. So the async IO loop is kept on a thread local. So async IO is attached, an event loop is effectively attached to a single thread. Async IO is not thread safe. And most uses of async IO are not thread safe. So you can't use the same event loop across threads or any of those async IO primitives like a async IO queue or anything like that. You can't use that across threads either. They're not thread safe. They are meant to multiplex and be used cooperatively, concurrently within a single thread. So it grabs the running loop and it creates a future and it says, okay, event loop implementation, call this callback later. So specifically it says, after this amount of delay, whatever your implementation might be, call set result unless canceled. And there's a couple of other little parts. And we're going to wait on this future. Now it's powered by generators and an event loop under the scenes, but we won't get too deep into the default Python implementation. But that's all that sleep does, is it says, hey, call me back later, and then I will wake up via my awaited future. Not really that complicated. Different async IO primitives work in a similar way. They all delegate to this event loop that they grab off of the current thread. And if you've ever used async IO before, a lot of times you probably have seen yourself setting a thread or implicitly setting a thread by doing async IO.run, which basically creates an event loop, sets the current event loop, and then runs the code, right? And there's cancel stuff, but we won't get too deep into that. So how does the event loop actually work inside of CPython? And it won't get into too much detail, but basically it works on a thread and it yields to each other's work. So it's known by other terms, cooperative multitasking. It counts on each piece to yield to each other. And at yield points, it yields to the next task that happens to be on its task queue. So most people, to start it off, they'll do an async IO run, and that has a couple of calls before it gets into the meat. Like that calls run until complete, and run until complete calls run forever. But inside of run forever, you see that it's literally a loop. That's why they call it an event loop. Surprise. And so it's literally a while true, do a tick of the event loop, a tick. Basically, run the code that is all resolved, whether that's resolved from a timer, resolved from some IO that has been accomplished, some network test that's been accomplished. So it basically says, run everything that's resolved and keep waiting and just keep doing that on this thread. So effectively, that's why async IO run is blocking, is because it's just a while loop spinning, running tasks and waking tasks up as they're needed. So it's important to understand for how I'll explain why how we created a distributed one nature. But in a nutshell, it's a loop and it runs things in a loop. So Python chose to, and we greatly appreciate them for doing this, Python chose to abstract that out. And so we can implement it. Now, like I said, it'd be very strange to implement it. And a couple of projects have, besides async IO, I think Trio has their own implementation. There's a couple of. But this abstract event loop has several things that you can implement in it. Now, it has the run forever that we saw before, like their run forever just calls run once in a loop. And it has stop goes. It has some task scheduling things. So it has like call soon for basically in queue a task immediately. Like the next time you do that run once, run it. Call later, what we saw with the sleep implementation after a delay. And then call at an absolute time delay as opposed to a relative time delay, and create tasks and some of these other things. There's also some other things more system-oriented around thread helping, IO, and other miscellaneous things that we won't really get into. And we personally, in Temporal, didn't implement this in our event loop implementation. But they're there to help for other asynchronous things. So like sub-process work, networking work, and going back and forth between the threaded world and the async world. And I won't get into details on that either. Okay, so take and memorize and like kind of stick that back, all of what we just talked about async IO. And let me take a second here to explain durable execution and kind of temporal in a nutshell so that it'll make more sense why we had to do what we did. So durable execution, right? It make sure your code is crash-proof. So how it does this is effectively we run all of the coroutines of a deterministic set of code that we call a workflow until they're all yielded. And then we send the stuff back up to the server. And then whenever it's done, whatever the side affecting actions are, they come back down and then we wake up the piece to resume from where it left off. But what makes it crash-proof is that all of those side affecting events that go to the server, if that thing crashes and it needs to get to where it left off later, we replay the memoized events, skipping over things that are already done, obviously. We're just replaying it, builds up the local state, and then it looks like it magically is resuming from the line where it left off. But it's not magic. So all these tools that do this durable execution, temporal, durable functions like Chris was talking about, All of them essentially use event sourcing to replay to get back to where you left off. So it looks like, oh, it technically is crash proof, but really it just memoizes side effecting steps, which means that workflows have to be deterministic and side effects have to be external actions. They need to be idempotent, but they do need to be external. So it's not just calling side effects. The power of the modern durable executions engines are you can schedule coroutines deterministically, which means that you can do many concurrent things, and we have to guarantee, in order to get replay, to get back to where you left off and get the local state and the local variables exactly the way it was on the next machine after this first machine crashed, those coroutines have to run in the exact same order. They have to be completely deterministic. Async.io and its default event loop are not deterministic for obvious reasons. It doesn't necessarily need to be. It uses system time. Some people end up using random, which we forbid in workflows and things like that. So we have to make sure also these async.io utilities are also deterministic. But luckily, they abstracted the event loop. So most of the Python code is deterministic until it gets to the event loop and you can have your own implementation. Like I said, it's pretty rare to write your own implementation, but for us, it made perfect sense because we have strict ordering of tasks that is not necessarily the case with the default event loop. So, and also the other thing that we need to know in workflows is, because the only way that workflows work is it's essentially sending a task of work, running a bunch of stuff until all the coroutines are yielded. So it's like 10 milliseconds of work. So these workflows that can run for weeks, years at a time, they really are just powered by little few millisecond bursts of go from where you left off until all the coroutines are yielded. So we need our event loop to tell us when everything is yielded, basically waiting on the server again, whether that's for a side effect execution or a timer or what have you. So that's durable execution kind of in a nutshell. Meet me outside if you want the larger nutshell form. All right, so here's a simple example of temporal in this case. So you have a workflow, it has a decorator, and you have the primary workflow entry point, and that also has a decorator. And you see that's an asynchronous call, and it returns a string. But you see here that the first thing is that we want to write a workflow that waits a week and then does a few things concurrently and returns the first of that currently. So we sleep for a week, which would be foolish to do in normal Python, but is very normal in a durable execution system. Sleeping for a long time, running things for a long time, no problem. So we sleep for a week, or the 7 24-hour periods. And then we use an async.io primitive to wait on the first completed of 3 things. And this is a pretty common need in all concurrent programming languages, to wait on the first of multiple things. And so we're executing 3 side effecting things, activity 1, 2, and 3. And we're telling it to return when the first is completed, and then we're returning the first one that is completed from the workflow. This has to be deterministic, which means that if this crashes when it's waiting or whatever, when it runs again, and let's say one of those activities has been resolved, it must be resolved in the same order. Let's say all 3 of them got resolved, but it picks one first. Python provides no guarantees about which it picks first in their traditional event loop. We have to provide that guarantee. So, and the timer survives even has to survive even process crashes. So this event loop now you're starting to see is not specific to the machine. That timer is not actually sleeping system time. It's actually just telling the server, hey, wake me up after so long. I don't care what server or what system it happens to be on. Wake us up after so long. So we had to write our own custom event loop, the purpose of the talk, right? So here is our implementation of call soon. If you'll recall, call soon is an abstract method on abstract event loop that basically says enqueue a task onto your task queue. And so in this case, async.io, you literally just have to instantiate the handle and put it on a list or put it on a queue. And this handle has a callback, and they basically say, when you are processing your task queue, hit this callback since it's now ready to be called. And so you can see below it that we had to write our own event loop, our own run once. But we don't run forever like async.io's default event loop. We only run until everything is yielded. So we maintain a queue of ready tasks that are given to us through the abstract event loop. We pop it off, we run the callback, and inside of that callback, the way that asyncio works, let's say that callback is doing lots and lots of different code. That will add more tasks, and that will enqueue more tasks as part of call soon and as part of many other things. So it's quite possible that this handle._run here at the bottom might add 30 more tasks, but that's fine. We want to run all of the tasks until it's completely settled and there's nothing ready, if you will. So it is very normal for tasks to create tasks, and they're actually kind of called handles or callbacks in the asyncio sense. But that's effectively how it works, and it's not really unique to Python. This is pretty common for cooperative multitasking systems in general. So back to what we did with sleep, back to what the sleep implementation in CPython is. Call later with a delay, set the callback. So what did we do? We implemented our own call later. Our own call later takes a delay and sends to the server, and then the server calls it back. This goes for any timers. So now if you use like asyncio.timeout, that starts the same type of timer via call later. So all of these are translated into durable timers that you could see like in the temporal UI. And you could see like, oh, here's a timeout timer, here's this timer, here's a sleep timer, whatever. And it's all magically works under the scene because the server wakes up the timer, not the local system like the traditional asyncio event loop. So that means that utilities magically work, which is awesome. So you could use like asyncio queue. Like we didn't write a special implementation for that asyncio wait for that you saw, the first finished of 3. We didn't write a special implementation of that. It schedules the tasks that it needs for that, and we just put them on a queue and then effectively complete those futures as they're completed from our server. So like here's an example right here of using asyncio event. All of this is powered via a deterministic or a durable event loop. So this event can totally wake up on a completely separate server, and it won't matter. It'll be completely safe and completely deterministic. Of course, if you use the regular Python default event loop, this would be in process. But this, the way that Temporal does it, all of that is shifted to an out-of-process server. So this might wake up on some other machine and it would be just fine. And it looks like magic, but now you'll know it's not really magic. And a little tidbit here, like we implemented this back in Python 3.7, and they since added features like a task group and all this other stuff, and we didn't have to do anything. It just worked because we had the abstract event loop implementation, and that's what most of these things end up delegating to anyways. So now let's get into a couple of the gotchas. There are a few gotchas, some with asyncio and some with what Temporal needs out of asyncio. So the first gotcha is cancellation. The way that asyncio decided to perform cancellation is it decided to do it mostly as an event. So you have some pretty interesting things like concepts of uncancel and cancellation stacks and stuff. And if uncancel doesn't throw you for a loop, it throws me for a loop. So what cancellation does is it essentially interrupts, it raises an exception at the next wait point of the code when you issue a task cancel. But if somebody swallows that cancellation error, it's like the cancel never happened. So as opposed to like some languages, like maybe in C#, you have like a cancellation token, or in Go, you have a Go context or something like that, that represent a cancellation as a state. Python instead throws it to be possibly caught and as if it never happened. So you can actually, in Python, unlike most cooperative multitasking systems, issue multiple cancellations and can uncancel. It can get a little confusing. So that doesn't really match what our server does. So if people catch and swallow cancellations, it's a big issue. Now, Python 3.8 did make cancellation base exceptions, so it discourages people from catching it, but it still properly hits their finalies, which is good because they want to do cleanup code and things like that. So that's one struggle is explaining that to users. And there are things like asyncio shielding that effectively don't propagate the cancel downwards inside the shielded code, but still throw outside of the shield. Because the whole point of cancellation is it's not canceled unless the cancellation exception is propagated outwards. The other issue. This means Temporal puts a lot of trust into the CPython implementation details. And what that means is that you saw I showed the CPython implementation of sleep in there. If they felt like, we're gonna add another await statement in there. A lot of our users would immediately become non-deterministic because they had events and code expectations built on a pre-version of one. They updated Python, and now the events are in a different order. This is just kind of something we have to live with and we have to test for. So for instance, here's an example. So that wait for call that you saw that was like the first of 3, it accepts a timeout. Previously, Python used call soon inside the internal implementation for that timeout because it's a relative timer. But it switched to call at because they used this new asyncio timeout feature. So by switching that, it actually switched to a different call on the abstract event loop, which luckily for us, we hadn't implemented that call because we discourage using absolute time inside of a deterministic runtime. So we implemented it and we were safe, but we have a possible future of being in an unsafe situation. So we have to keep pretty close tabs on the CPython implementation of asyncio to be safe going forward. Another gotcha. This is more of a gotcha about asyncio in general and not specific to temporal or even really specific to workflows. And that is, it is too easy to block the asyncio thread. And people do it all the time, to the point to where in our activities, the side effecting form, we discourage people from using async because they're not sure that some transitive code further down isn't going to accidentally block the thread. And if you block the asyncio thread, if you do anything synchronous in an asyncio thread, you've gummed up the whole system because we saw it's an event loop. And if that isn't returning from that run once or from that specific handles run, then nothing else on the asyncio loop can run. So it is, unless you're absolutely sure that you're async capable, which we're completely sure in our workflows because we have a custom event loop, don't necessarily run async. Stay in the threaded world, it's still okay. And asyncio, I mentioned here, they offer a debug mode that'll catch, like if it hadn't been awaited within 100 milliseconds, which can kind of help you catch some of these. But that's not really that's more of a reactive than a proactive. So just be cautious. This is more of a general asyncio warning and not specific to custom event loops. And then finally, our last gotcha that we hit was garbage collection. So I mentioned that asyncio event loops and tasks are powered by generators underneath. Well, it turns out that the Python garbage collector, when it needs to collect from a generator that never completed or a task that never completed, it raises a generator exit. And a lot of us have seen these, right? And that can trigger finally clauses and things. But what would happen is we have this workflow cache, and we use this workflow cache as an optimization. That replay, even though it takes a few milliseconds, we prefer to avoid it to get to where your code left off. So we keep workflow instances in cache. Well, once the cache is a little full and we need more space, we delete it out of the dictionary, and that will trigger a Python garbage collection. And we thought just deleting it out and letting the list of possibly half-complete asyncio tasks just get garbage collected would be fine. But what would happen is generator exit would be raised in there by the garbage collector in whatever thread that it was GC'd out of, which wasn't even in the thread where we run it because we run these workflows in separate threads, even though they're their own event loops. And so it would trigger people's finally clauses, which we try and tell them, if you're using temporal specific stuff, it won't have side effecting things anyways, but it'll trigger their finally clauses running in the wrong thread, which will get really confusing because it looks like one workflow code is doing another workflow code's thing. So once we finally figured out that garbage collecting incomplete tasks is unacceptable, we recognize we actually have to explicitly cancel all tasks on our way towards what we call eviction, cache invalidation, if you will. We have to wait and let those tasks finish, or we can't remove it just because garbage collecting a half-complete task is a problem. So those are the main 4 gotchas. And to sum it up, you have asyncio provides a nice abstraction if you want to customize the event loop, which is really cool for temporal and other durable execution engines because we do want to customize the event loop for timers and for determinism. But there were a few gotchas along the way. So that's my talk. I hope I gave a little bit of detail and kind of how asyncio works. I don't know why you would write a custom event loop, but we did, and it was kind of cool.